So what we'll do? Okay, so hey Vivek, did you do any quantum?
Yes, of course.
You have done quantum. Okay.
Yeah.
This was at undergraduate or in the recent?
Basics in undergraduate, then I went up to a little bit of relativistic quantum mechanics.
Okay, so you are
Did
you are also.
yeah, a little bit, I would say.
We might need some second quantization down the road. Don't you have had quantum, right?
Yeah.
Yeah, so we should be okay. I mean, I'll give you enough uh, prep stuff on that.
Okay.
So what we'll do, you see, we also have an interesting problem, which which is for the first time, of course. New problems are always interesting. Um, the classroom in which the class is supposed to be held is not particularly helpful right now or useful right now because projection system is not working there. Our so-called tech people did some new tech and then they screwed up. So as a result, we are not able to use any PowerPoint, anything that can be projected. But it's fine, of course, for using the Blackboard. So I was telling Tony, maybe what we'll do now until it's fixed up is we'll use Zoom when we don't need to use the Blackboard and use the classroom when we want to use the Blackboard. Because not everything can go on the Blackboard, not everything can go on Zoom either. And the unfortunate fact is, which I just learned, that this will continue for several weeks. Yeah, it sucks. That's what Nicole told me. Nicole is the one who's supposed to fix it. Nicole basically, she's supposed to have it fixed, but Nicole said parts have been ordered on 22nd of January, and we all know how rapidly UB acquires parts. So my thought was, okay, so are we going to screw up this whole semester, or are we going to get something mid-semester? I honestly don't know. But let me pull up what I have. So Tony, I'm going to repeat a little bit of what I have, which I already did in class. This is the one, I think. Okay. Now let me project it. Can you see the screen?
Yes.
Okay. The screen has nothing to do with doing statistical physics. It has nothing to do with doing much other than the fact uh, to make the point that people are publishing rubbish most of the
Yeah.
time. I was shocked to see that hyper publishing has become an official term, and publishing 40 to 60 papers per year is apparently not unheard of. This is certainly not normal. A paper a week almost or more is not normal. So why did I pull up this slide? I pulled up this slide only because it is important to be not normal, but not normal in a good way, not in a bad way. In this case, the lesson is that, when we all do science or any subject for that matter, it is super, super important to make sure that we are actually doing something that is worth something to somebody else. If that is not the case, the question can be asked as to why is it important, especially in physics. I mean, this question cannot be probably asked in mathematics, where many things don't seem important, but we do it because it's a necessary step to a deeper understanding of how numbers behave. Not so in physics, it has a relevance. So it's really important, I think. I mean, I have a collaborator who I respect a lot, actually. I've published a few papers with him. He publishes more than 40 papers a year. And I don't know how he does it, but he does. Of course, he collaborates with about 60 people, so that helps. So this is stuff that Tony and I did a little bit, and I'm going to quickly go over it because it's not that important. It's just to get our conceptual bearing straight and more for Vivek to sort of share my thoughts on this. So development of understanding of a topic is sort of like building a dwelling. You're building a house. Initially, it may be a shanty or a little hut, or maybe a small house, and sooner or later, it can develop into a palace or a town or even a city. Thus, telling the story of dynamics of many body systems is equivalent to covering more than, in this case, a metropolis. It is almost one of covering a nation itself. Dynamics is pretty interesting. I was very interested in dynamics as a young kid almost. And so when chance came for me to do physics, I wanted to do either of two things. I wanted to do astrophysics or I wanted to do dynamical problems. Astrophysics was not to be. I didn't get accepted to the right places at the right time. So I figured, well, dynamics is not bad at all. And I got an excellent advisor very early in my career, a PhD. And I wanted to learn dynamics, but I realized that it was impossibly vast. So my advisor instructed me that if I want to get out quickly, which I wanted to, he and I discussed that we should get out in less than 3 years. I should get out in less than 3 years. And he pretty much said, okay, we'll try if you really work hard. I said, fine. But then he said, you listen to exactly what I tell you. And you do exactly as I tell you. And don't deviate from it. And work as hard as possible, all of which I did. And I got out in less than 3 years. But what was fascinating was when I started looking into materials that interested me, I got a scolding. And I got a scolding many times like that. Ultimately, I learned never to do that while I was a student because his point was you are deviating. You have wide interests, don't go everywhere, just stay focused, get it done. I'm not asking you to read umpteen papers because they are not relevant for you right now. You can read them later. You first form your own understanding of the subject. And once you have your own understanding, once you can see a problem through your own eyes, through your own brain, then you'll be in a much better position to read papers and analyze what is good and what is not. And that struck me as very unusual advice, but it has turned out to be very good advice, at least for me. So I don't read papers, I jump into a problem. And then once I've made sufficient progress, then I might go around looking for papers most of the time. Anyway, so this topic of dynamics is a vast topic, is my point. And there is no course in the world, or there'll never ever be a course in the world, which, let's say, is even 2 years long, that will even be able to do justice remotely to what dynamics is. And I'll be the first one to tell you I know very little dynamics. I know what I don't know. Okay. And if I list that, it'll be a very, very long list as to what I don't know. So the idea is that you'll never know much. You always have to work with people who know a little bit differently, and that's how you attack these problems. The other important thing I was telling Tony on Tuesday is it's so important to remember history or learn history. Most problems that we look at, in my experience, have been solved by someone or the other. Excepting we ignore them, it is hard to find out who has solved something 50 years ago or 30 years ago, or sometimes a few thousand years ago. And we end up rediscovering the wheel in the process. Nothing wrong with it, other than, we don't get as far ahead as we should. So I point out here that Newton's laws are not by Newton. Newton's laws were first, and the definition of force was first introduced by this gentleman, Maharishi Kannada, in 6th century BCE. The 6th century BC, that is. Even law of gravitation was known to Bhaskaracharya and Brahmagupta back significantly before 17th century. I don't have the date on this. And even calculus arrived in India 250 years before Newton and Leibniz. It's around late 1300s. And, Newton had access to that because Jesuit priests had traveled to Europe in the meanwhile and had taken some of those insights along. So mechanics as we know it, dynamics as we know it, has been around for a long time. We may not know what all has been done. So let's look into specifically non-equilibrium studies. Non-equilibrium studies, by and large, mean that you are doing studies where you start off with some relationship with equilibrium. So this particular course is more or less going to emphasize non-equilibrium celestial mechanics, which is what we have on the left column here. And the other part, which is also many particle, many body, many degrees of freedom, also non-equilibrium, is this nonlinear dynamics of systems with many degrees of freedom. I always think about this area as a relatively new area because nonlinear dynamics itself is an enormous subject. And when I say nonlinear dynamics itself, I mean nonlinear dynamics of one or two body systems is an enormous subject. I mean, there is a big fat book by Francis Moon called Chaotic and Fractal Dynamics, if you're interested. Francis Moon was a very famous person. He was a professor at Cornell. He's still alive. He's retired now. And he wrote this massive book, which presents nonlinear dynamics as a subject extremely well. And it's an old book. In more recent times, Steve Strogatz, also from Cornell, has written a very nice book, but not as comprehensive or as easily readable, maybe, as Moon's book. But I'm not going to go to that part of nonlinear dynamics of one body systems, or represented by a single equation with 1 degree of freedom. I'm not going to do that. I'm only interested in many body, and one body and many body are very different in many ways. And a few body is a mess. So I'm more in the many body end. So nonlinear dynamics started originally with the wave equation, actually. Now, wave equation is a term that is a little bit abused because when we say wave equation, we know wave equation shows up in electromagnetic theory. We know it shows up in acoustics. We know the Schrödinger equation is basically a wave equation that gets us rolling with the wave function in quantum mechanics. Elasticity theory is tied to waves. Seismology, oceans, fluids, we can go on and on. Waves are everywhere. However, that doesn't mean that all waves are described by what we think of as the wave equation, which is this del T2, del 2, U del T2, and then grad square of U. And then in between is the c squared, the velocity of the wave. That is a simple linear wave equation. However, if c has a dependence on factors on the medium, for example, or if the wave has dissipation terms, still a wave, accepting it's not as simple, you immediately move over to nonlinear wave equations. And nonlinear wave equations immediately pose real difficulties for the most part because they're hard to solve. And in fact, these nonlinear equations were first pursued around the same time as the wave equation was pursued, sometime in the 1600s to 1700s time frame. And it turned out that people were looking for very, very large waves to emerge as solutions to these nonlinear wave equations. That was of interest because the ships that were sailing off from Europe were unknowingly trying to come to America. They were crossing the Atlantic Atlantic is a very rough ocean, and the large waves caught most of the ships. The kings and queens were very unhappy, and all the physicists and mathematicians of the time were pretty much encouraged to look into nonlinear waves. That's the history of it. And that led up to the first integrable equation here that you see in nonlinear equations bullet, and that is the Korteweg-de Vries equation. I will come back to this equation later. Then there is the nonlinear Schrödinger equation, which is also a wave equation, but with some nonlinearity. And then there is another wave-like equation, Sine-Gordon, and Toda is a lattice equation. These are all integrable systems. These are the main integrable systems. There are many cousins of these equations that are also touted as integrable systems. Integrable systems are good because you can solve them. However, the more interesting problem concerns what we'll talk about as non-integrable systems, which cannot be integrated out, hence they're difficult to solve. That doesn't mean that they cannot be done. It just means they are horribly difficult to do. Okay? So integrable systems are relatively straightforward to do if you know the right trick. Non-integrable systems, on the other hand, present all kinds of complexities, but that doesn't mean that they cannot be done. They can be done if one is sufficiently insightful in looking at them. So that's possible. So there is also the dynamics and kinematics of materials and complex systems, and among them, come many things. For example, weather prediction, meteorology. Weather prediction is done in a very light-hearted way. We have no ability even in 2026 to say what the weather would be like tomorrow. We really don't have any ability. What we do and how we know about tomorrow or day after tomorrow is we actually have aircrafts. Every aircraft that's in the air records weather data on the spot continuously. And that data is fed into computers. And there are some standard models. There's a US model, there's a European model, there are other models, I'm sure. And these models collect that data at time t. They collect the data at time t+1. They calculate the matrix that would act on the data at time t to give you t+1. And use that matrix to project what's going to happen tomorrow and day after tomorrow and day after day. So that kind of calculation, which is, of course, very extensive, very detailed, very useful, because if there's going to be a tornado tomorrow, you'd rather not go out. It's very useful. That kind of calculation is called this DMD, that acronym I've used here. It's called dynamic mode decomposition, DMD. This is another example where I didn't even know about DMD. And I had I still have actually, a very enterprising young collaborator, Edgar Avalos, a Mexican physicist, a former postdoc. And Edgar sent me an email saying, do you want me to try this problem with DMD? I said, what is DMD? And that's how I learned dynamic mode decomposition. So I read up on it, and indeed it is basically just that. It's like x prime equal to ax, right? All these are matrices, and once you know A, you got it, right? And you got a very good result using this approach. It's a very powerful approach if it can be done. Anyway, so what I'm trying to say is that when you have really complex materials, complex systems like the climate or the ocean, how do you even predict? Well, there are ways to predict, okay? And this is one of the ways that I know, so I thought I'd mention. Okay, so I talked about non-equilibrium statistical mechanics as a big basket, and then I moved to nonlinear dynamics. What is special about the right column, everything I've listed on the right column, is that temperature is not there. Okay, so in all these systems on the right column, nonlinear dynamics of systems with many degrees of freedom, wave equation studies, nonlinear equation studies of integrable systems, non-integrable systems, and then this complex systems. In general, temperature is not in the picture. In fact, there may not even be a definable temperature. For example, one complex system can be the society. Okay, you are living on a campus, let's say. The campus itself is a society. People are interacting with each other. Teachers are interacting with each other. Postdocs are interacting with each other and with others. So if you have some way of characterizing these interactions, let's say, if you are being mean to me, I'm mean to you. If you are being nice to me, I'm nice to you. It can be something as simple as that. And then you can think about every person as an agent. And as agents interact, they have this kind of role that controls how they interact. You can evolve the society in time using agent-based models, and thereby be able to describe society. There is no real temperature in these systems. Temperature is a very simplifying concept. You have a system, temperature is the same throughout the system, and that's a great simplification. Whereas in society, if you want to bring in temperature, you will have a heterogeneous temperature. One area may be very hot, a lot of people enjoying talking to each other. One area, people don't even know the next door neighbor. It will be a very inhomogeneous temperature system. In fact, most complex systems are very inhomogeneous temperature systems. And so they're basically a thermal system. They're not thermal systems. The one on the left column here, I'm thinking about thermal systems. And thermal systems have interesting features in them that allow for some simplifications in calculations. That's the reason why thermal systems are special. And non-equilibrium statistical mechanics traditionally concerns thermal systems mostly. So the yellow highlighted area is where we'll start. So we'll start digging into this whole metropolis or country of different areas. Sometimes very independent areas, governed by different kings and queens, right? And nobody knows the whole thing. So we'll start with this particular neighborhood, and that is rigorous Hamiltonian-based approach to study dynamics of systems. So that means you have a Hamiltonian. That means energy is conserved. That means you have some method that can be used to evolve the system in time, presumably something which is somewhat analytical. Vivek, you are okay there?
Yeah, I'm okay. Just camera is not working
Camera is
properly.
okay. Okay, so how do you solve these problems? This particular line of work that I'll start with, rigorous Hamiltonian-based approach to study dynamics, was begun by a gentleman by the name of Robert Zwanzig. Zwanzig is spelled Z-W-A-N, Z-Z.
Yeah, I have his book.
Z-W-A-N-Z-I-G. You have Zwanzig's book?
Yes.
So Bob Zwanzig was a professor at University of Maryland. This is the book
Yes.
actually.
Yes, this exact book.
Yeah. And Bob Zwanzig was one of the early pioneers of trying to solve these problems exactly for thermal systems. And it's called non-equilibrium statistical mechanics. Tony, for you, I don't have a PDF of it, by the way, but if any of you do, then feel free to pass it around. It's an excellent book, very rigorous book, not simple to read, but it's a good book. It's really one of the masterpieces in non-equilibrium statistical mechanics, as far as I am aware. So, unfortunately, though, the techniques developed at the time by Zwanzig and his co-workers at the time, 1950s, late 1950s, early 1960s, they were not very user-friendly. Okay, you pretty much had to know the answer before you could solve the problem, which is typically the case most times anyway. You cheat and figure out the answer, then you see, oh, okay, fine, I need to tweak it here and there. But Zwanzig's approach was not easy. So it turned out that in 1965, a Japanese physicist, his name was Hajime Mori, M-O-R-I, Mori. Hajime is H-A-Z-I-M-E, Hajime Mori. Hajime Mori wrote 2 papers back to back in that Japanese journal, Japanese Physical Society journal, whatever the name is, I forget. I think it's called Journal of the Japanese Physical Society, I think. JPSJ. This back-to-back 2 papers, they are combined, they're about 50 pages long, if not a little more. Very, very big papers. And Mori presented a very well fleshed out technique to solve the equations of motion, but in a canonical ensemble. Equations of motion where the temperature is fixed. So temperature, volume, number of particles fixed, TVN ensemble. Now, Mori's work, unfortunately, was not quite as well received as it should have been, because Mori's work took Swanzig's original work and essentially kicked it up to a point where his vision was that anybody can pick it up and start working on it. You didn't need much, okay? It was literally like a ladder to go from here to there. Problem was that Mori's paper was not easily understandable. And the other problem was that the way Mori presented it, it didn't give enough examples to see through the applications. You see, a method may be a great method, but if you can't apply it anywhere, what good is it? You have to be able to take the method and apply it. Now, if somebody is not able to apply it because he or she doesn't understand the detail of it, then that becomes a problem. So Mori's method quickly gained the reputation of being not worth doing. It's too difficult. Forget about it. The papers were ignored. Until in the late 1970s, early 1980s, the gentleman who actually was my thesis advisor, he took a fascination for them. And he decided that he could do better than Mori. And he did. And he made it into a much more smoother ladder, almost like an escalator, where you can pretty much sit and move, right? It's not quite as simple, but many notches in complexity below Mori. And to do that, he sacrificed some of the generality that Mori had brought in. He made it more modular. He said, okay, you want to do this, you try it this way. You want to do that, you try it that way. It was more like that. Mori gave you the whole package. Okay. So this change helps some. And so many people, after his name was Lee, M.H. Lee, M. Howard Lee. After Howard's work, many people began to kind of take up this approach, but still not as many as one might expect. Still not as many. Well, tells you when calculations are very, very difficult, not too many people want to do it quite that way. But here the bonuses are fantastic. What you can get out of it, if you can solve a problem, is outstanding. And so one of the things that I think I'll do is I'll introduce the formalism, but that is usually not the biggest issue. It is how to use the formalism that is the biggest issue. So we'll spend some time in learning how to use it, because learning how to use it is where the dirt is present. That's where you have to get your hands dirty. Okay. The other way of doing non-equilibrium statistical physics is somewhat older, goes back a long time, early 1900s. Einstein's time, when Einstein introduced Brownian motion. And this is the so-called stochastic approach. And it's a powerful and convenient way to study dynamics of systems, stochastic approach. What is the word stochastic all about? Okay. Why is stochastic why does it make it so convenient? The reason why stochastic approaches are so convenient, because in a stochastic approach, by definition, when an interaction happens, the memory of that interaction is lost immediately after the interaction. It's like So it's an instantaneous event in stochastic dynamics. So for example, let us assume that I'm interacting with the two of you, but the moment the class is over, I will no longer know that I interacted with the two of you. All that you will see is that my trajectory is a little bit different because I'm talking funny because you guys were with me. Okay, that's kind of like that. So the Langevin equation characterizes this stochastic physics. It's a Newton's equation, but effectively with a friction term and with a, instead of having a normal force term, it can have a normal force term, dp equal to F. But it also has a many body force term. So imagine then that P dot equals, let's say, minus gamma V, V being velocity, dissipation term. Gamma is your friction term. This friction comes from that stochasticity. And then you have a many body force term and maybe a one body force term, external force term. So that's typically the structure of this Langevin equation. And then there are the master equations. Master equations are literally, as the name says, some rate of change of some process is connected to what happened before, what happened after, maybe some other effects. You can make these equations up as you go along. Boltzmann equation is also a kind of master equation. They're all belonging to the same bucket, if you will. Diffusion equation is a cousin. Diffusion equation, the derivatives are a little bit different than the wave equation. First order derivative comes in. It also is very useful. Diffusive processes are very important. For example, somebody tells you something, a joke, and you want to share that joke with others. So that joke begins to diffuse through your society. Right? Similarly, you can have, for example, a poisonous gas introduced into a room. How does this poisonous gas spread? What is the probability of finding gas molecules in this spot, that spot, that spot? So typically that's what diffusion equation brings us. But diffusion equation itself is not necessarily stochastic. There is a stochastic version, there's a non-stochastic version also. Now, the reason why I put the highlight on the rigorous Hamiltonian-based approach and not highlighted the stochastic approach is not because I won't do the stochastic approach, but I want to come to the stochastic approach from the rigorous approach. Because ideally, in the rigorous approach, if I can do the correct approximation, I should be able to also recover much of the stochastic approach. And then, of course, we can go back and do it properly as traditionally done as well. So we have two pathways into the stochastic system studies. Another very important way to study systems that has become particularly relevant since 1959, 58, 59, is this dynamical simulation-based studies of many body systems. We often forget how new it is. So just to share with you how new it is, bless you. I had organized a meeting in Korea in 2001 or 2, I don't remember. And one person I wanted to invite badly is Bernie Alder, A-L-D-E-R, Alder. Bernie is B-E-R-N-I, Bernie Alder. I'd heard his name, I'd read his papers, I really wanted to meet him. So I sent an invitation, I had some money around. I sent an invitation to Bernie Alder to come to Korea to this conference. And the title of the conference was Slow Dynamics in Nature. And the reason why I badly wanted to get Alder, because Alder was the first person in the world to do molecular dynamic simulations. In fact, there is a paper called Alder and Wainwright, 2 papers, around 1958-59 from Lawrence Livermore labs. And Alder and Wainwright simulated a hard sphere gas, and they got the correct thermodynamics and everything. And in fact, it was a privilege to, of course, meet Alder. He did come. He's passed away now. He was already in his late 70s at the time, but he lived till his late 90s, and he was very active even till the last part of his life. But Alder was the first person who introduced molecular dynamic simulations. And then there was an Indian guy and his name was Anisur Rahman. Anisur Rahman, Rahman. And Anis Rahman took the Alder Wainwright work and made it into literally a technology. Okay. And he single-handedly did it sitting at Argonne National Labs. So you can take a system, let's say you have some chemical that you have, you know the potential to describe the interactions of the molecules or the atoms. You put the potential in, you set the temperature, you set the number of particles you want to simulate, you set the initial conditions that you want to start from, and you run it. And that's how I learned molecular dynamics back in 1984. I had Anis Rahman's code. And the reason why I had Anis Rahman's code was because my teacher, John Ray, was Anis Rahman's collaborator. So Anis encouraged that the codes be tried by all of us idiots so we could try to break it so we could fix it. And so that's how I learned to do MD in those days, back in 84. And I had the privilege to actually interact with Anis. So in addition to Alder, because when I had troubles and John wouldn't be available, I could actually drop a message to Anis. In those days, email was barely coming around in 1984. So telephone was easier. I would call him up and ask for help. And he was always very gracious. Unfortunately, you don't hear his name as often as you should because he died very young. In fact, he died before I finished my PhD. But American Physical Society's Computational Physics Prize is called Anis Rahman Prize, recognizing his contribution. So anyway, so dynamical simulation-based studies were started by Alder and then by Rahman. And after that, now Sandia has a code, which is freely available to everybody. And this code is called the LAMPS code, LAMPPS, I think. I forget the large something. It's freely available, LAMPS code. You put in the potential, you put in the conditions, you study what has to be done, everything is documented, and you run it. So nowadays, molecular dynamics is pretty much run using the Sandia code because it is so well tested and well documented. And everybody can check everybody's work. I won't do it in this course because nowadays there is no reason to do it. Documentation is so good that young people, they simply go to the sandia.gov site and download it and they can get rolling. You just have to make sure that they know what they're doing once you get going. There was a time when I taught this class and I actually had taught this code and how to use it, but that was back in the 90s. Anyway, the part I didn't discuss here is the fluid part, and that is, of course, the Navier-Stokes equations. And Navier-Stokes equation is the following structure. There's a viscosity, the dynamic viscosity that is defined, which is a constant in Navier-Stokes equation, mu. This is the velocity field, gradient squared of the velocity field. And here you can see that the density of the fluid, du dt, is defined as that. Now, so this is obviously a derivative which is a structured derivative. That's why I have capital D. I don't want to flesh it in or get into it because I won't be touching Navier-Stokes. I just want to point out a few things about Navier-Stokes. Navier-Stokes is not an energy conserved system. It's a dissipative system where viscosity, the equivalent of friction, comes in. So if two layers of fluid moving, the top layer is grinding against the second layer. The second layer is grinding against the third layer. So that's where the viscosity, mu, comes in. Mu is treated as constant in here. That's a simplifying factor. And also, this equation is strongly nonlinear, so it is difficult to solve. Normally, one solves it using numerical approaches. But Navier-Stokes equation is tucked in there. By the way, you can derive Navier-Stokes equation starting from a Hamiltonian description of the system by using the sufficient approximations and simplifications on the Hamiltonian equations to get here. In fact, that's how it was derived. And there is a series of papers based upon how the Navier-Stokes equations came into being. By the way, if you are ever interested in learning about the Navier-Stokes equation, my advice is you take the fluid dynamics course offered by the mechanical engineering department, because mechanical engineers are the ones who have really refined the art of studying these equations. Physicists have not. There are very few physicists who work on it. Physicists have developed some techniques for solving the Navier-Stokes equation, which are very novel. For example, there is the lattice-Boltzmann technique. So there are standardized codes like the LAMMPS code I mentioned from Sandia. Lattice-Boltzmann was developed at Florida by a gentleman by the name of Tony Ladd, LADD. And it's widely used. So there are other ways. They're not easy. None of these are easy, but they can be done. Okay. So let me now move on to perspectives on complex systems, dynamics of complex systems. Because thus far I've talked about many body systems where you can describe things with a potential. So you can pretty much structure the description of the system very well. But complex systems are really a problem. Okay. What are complex systems? Well, complex systems can be like flow of a river. River flow, although it may be just primarily water, but it has a lot of physics in it. And rivers are the lifeline. Rivers keep us alive, right? If you don't have rivers, if you only have salty water, Lord help you, you won't be around for very long. So rivers are in fact, there is a lot of work on river networks in various places. River networks also follow certain structural laws, scaling laws, and so on. So there is an enormous amount of work done on how river networks are like. And you can take rivers in many, many parts of the world, and you can show that more or less those generic features in the studies of river networks actually shows up. Anyway, so next time you fly on a plane and you see rivers down below, think about this, maybe look up a little bit about this river networks. One of the pioneers of the work on river networks is somebody who I'm very fond of, and I'm also a good friend, much older than me. I'll put down the name here in a box just so that you can look him up and look up his work. Is Jayant Manavar. Jayant Manavar used to be at Penn State, but he's now in University of Oregon. And he has written a series of very original papers with his collaborators on scale-free river networks and all that. Anyway, then there is, of course, the very famous problem of avalanches. Physicists have avalanches, and nature has different avalanches. Physicists' avalanches are much simpler, but nature's avalanches tend to be quite complicated. And sort of like weather prediction, where I said how the airline data is used to predict weather. This avalanche prediction in real life goes like that. So, for example, if you're predicting avalanches in the Alps, you continuously collect data on the conditions of the terrain and the temperature and the humidity and the wind speeds, wind directions. All of these are collected with sensors. And that data is sent off to a little lab in a very famous place, which is not known for studying avalanches, in Switzerland. Can you guess the name of the place? Very famous place, Davos, of all places, where all the World Economic Forum is held. It is in Davos. They have a little lab maintained by the Swiss government that collects all this data, and it has its DMD type matrix, and it predicts what's likely to happen. And they would publish the avalanche risks continuously online for every other day. That way they can help the skiers on the Alps so they don't get affected. Another problem that unfortunately I won't be able to touch upon in a course is glassy dynamics, dynamics of glasses. Dynamics of glasses is a truly, truly fascinating topic because glasses are, by definition, frozen liquids. A glass is a frozen liquid. Liquid flows. So question now arises whether a glass flows. And the answer is yes. And then the question is, how does it flow? How quickly does it flow? And the answer is that can be decades. It's maybe 1 micron per decade, maybe a little more than that, maybe a little less than that. But it does flow. I told this story in the first semester, so Tony might remember. As a graduate student, you acquire cheap furniture because furniture is expensive. So I acquired this cheap 1970s style furniture, which was meant to keep the stereos. Basically, I had a stereo, this, that, speakers, blah, blah, blah. And in this cabinet, I could keep my stereo components. And in those days, I had a record player also, like you could play the 33s and the 45s and so on. And that one had a glass door. So the components of the stereo didn't get dusty easily. It had a glass door. So subsequently, after I left graduate school, we moved to many places and eventually bought a home. And I couldn't throw it away because I should have thrown it away, but it was still in good shape. And initially I kept stuff there. Then whatever happened, I took the glass door off and I put the glass door against the wall in my basement. So it was like basement wall is vertical, glass door was resting like this. And then, as luck would have it, I forgot about it. So after about 15 years, it occurred to me that I should move that glass door and put it back on the cabinet again. And as I touched the glass door to move it, it exploded. And I was not only filled with glass shards myself, the entire basement area that was accessible, that means the door didn't block it, was filled with glass shards, teeny tiny ones. And I realized what has happened. The glass was sitting in a quasi-equilibrium state when I put it there, but it was way out of that quasi-equilibrium state when I picked it up after 15 years. And that's what did it. It exploded. Its energy was too high. It was no longer at an energy minimum. Luckily, nobody was hurt. I just had glass coming out of me for several days. Other than that, there was no real problem. But this is how they are. Glassy dynamics can be very, very slow. And people have studied this problem greatly, in great detail, with great dedication. Glacier flow is very similar. Gas flow, magma flow is another very important topic, dust flow, traffic flow, current flow, continental drift. Continents are drifting. In fact, the fact that continents are drifting, we are living at a very special time with regard to continental drift. I don't know if you guys know, but Africa is splitting up. Yep, in the Rift Valley, which is around Ethiopia and Sudan, that area, Africa is splitting up, and an ocean is going to form as Africa breaks apart. So some million years later, you'll have part of Africa, another part of Africa, separated by an ocean, and then you have the Arabian Peninsula, and then you have the Asian area. Okay, tectonics at work. All right. So anyway, so just moving on, I mean, I put this picture in just to point out that the viscosity mu doesn't have to be a constant. In fact, there are scenarios where viscosity mu becomes dependent on X and Y and so on. And those cases where mu is not a constant, they're called non-Newtonian liquids. You'll find oftentimes papers titled non-Newtonian liquids or non-Newtonian fluids. That's basically what it means. That means that mu is not fixed. Okay. A very, very important and fascinating area of physics is the physics of shocks. And shocks can be tsunamis, shocks can be from earthquakes, shocks can be from bomb explosions, bullet penetration, comet impact, cratering, all of these are shock processes. What is special about shock processes? The systems are subjected to extreme compressions uh, over very, very short time scales, and therefore they behave differently. Strong forces come into play, and so they behave very differently. I talked about social systems already. Biological systems are also very, very interesting. There's a lot of work now on swimming of various bacteria and so on in fluids. Dynamics of how neurons operate, sensory networks work. Locomotion. There's a guy in Georgia Tech, Dan Goldman, who studies locomotion. How does a living being walk? Or how does a living being crawl? Or how does a snake penetrate into soil? These are fascinating problems because the dynamics of these processes that are naturally seen are by no means simple. In fact, the skins of these snakes that can go under the sand are very specially structured, has had few billion years to evolve, right? So they're very specially structured. So finely structured, in fact, that the kind of roughness we would feel if we had to stick our hand in the sand and try to move inside the sand is not what the snake feels. The snake has very different kind of skin. So people are studying these systems. So this is how that's why I said dynamics is like a whole country. If you think in that analogy of homes and palaces, diffusion processes, animal migration, disease spread, rumor. I mean, you can go on and on and on, right? So dynamics, when we say that we're going to study many body dynamics with this, uh, I think we should be very modest and we should say, you know what, forget about dynamics. We're going to study Hamiltonian dynamics of many body systems in canonical ensembles. Then you are still talking about a vast field, but you're not talking about whole nation. You may be talking about a neighborhood, or maybe talking about a small town, but an important town. Okay. The starting point of dynamics is the Liouville equation. Now, Liouville equation owes its origin. So I basically stole this from David Tong's page. David Tong is a professor in Cambridge, and you may know about Tong's website. He tends to post his lecture notes very nicely in LaTeX, and they are typically compiled almost like a book. I don't know if he has actually published his books, but David Tong's lecture notes I find quite good. What do you have there?
So this is Statistical Mechanics Notes of David Tong.
There you go.
Yeah.
DC Tong. So
Yep.
Tong is very nice. Tong's lectures also are very, very nice. I enjoy looking at his stuff from time to time. So David Tong does give a very simple and elegant description of dynamics. Talks about the fact that the phase space volume is conserved in a conserved system. That doesn't mean the phase space volume is fixed. The volume is conserved. The shape can change as, let's say, Q, a function of t, and P as a function of t evolve in time in QP space. You can imagine that the volume of this phase space bundle that describes a system, or a phase space lump that describes a system, evolves in time. The lump's properties, the geometrical properties can change, but the lump's volume is fixed. And that's the main point about Liouville equation, about the phase space conservation. And therefore, this del rho del t is equal to 0, or d rho dt is equal to 0. And then if you think about rho, this density function in terms of Q and P, you essentially arrive at this structure at the end of what is called the Liouville equation. So in this case, you can just take the rho away and you can think about any other variable A, let's say. So it's like del A del T or dA dt is essentially a commutation between A and rho. if you pay attention to the fact that this is PQ and this is QP. So if you write it as PQ, it'll be rho H minus H rho. Okay? So del rho, del Pi, del H, del Qi minus del H, del Pi, del rho, del Qi, which is a Poisson bracket.
Yes.
Okay. So the structure of the Liouville equation is that time evolution of a variable a of t, let's say dA dt, is essentially the Poisson bracket of a comma h. That's what Liouville equation is for simple stuff. But what I want to add here, which Tong doesn't get into to avoid trouble, is that the Liouville equation is your passport to not only getting Newton's equation, it is also your passport by changing that bracket from Poisson bracket to commutator bracket of deriving the Heisenberg equation of motion, which is the operator evolution equation in quantum mechanics. And then if you further change the bracket, you can get to relativistic equations. And then if you further change the quantities, you can even get to Einstein's field equations. All of them have the structure of the Liouville equation. So Liouville equation is therefore a very, very important equation which reveals the structure of time evolution in nature as a broad general problem. This, I think, is remarkable. I haven't read too much stuff written on it, which is penetrable, because oftentimes, the notation used and the language used makes it very difficult to read and follow and intuitively understand. I don't know of pieces of work that discuss the generality of the structure of Liouville equation, but it is a very general equation of motion. There is another piece, harking back to the topic I raised here, the highlighted area, rigorous Hamiltonian dynamics. There is another piece to studying this other than the Liouville equation, which gives us the equation of motion. And that is the concept of linear response. What does linear response mean? Linear response has a very simple meaning. It means, suppose I take this little thing here, which is the lid of a bottle, and suppose I hit it. If I hit it, yeah, it makes a racket, but after a short time, this lid is just the way it used to be. In other words, this hit is gentle enough to not have affected the lid, right? So that would be linear response. That means this perturbation to leading order does not affect the system. Okay? So if I now, instead of doing this gentle tap, if I hit it with a hammer, you know darn well that this lid will be squashed. That would not be linear response. Then we would enter the domain of non-linear response, where the energy imparted to this at t equal to 0, when the perturbation is given, is so much that the system's Hamiltonian gets affected by the perturbation. So our job then is to sort of understand what is this linear response. And that's why I thought I'd throw this in. I've actually taken this paragraph from Balakrishnan's book. I'll share PDF of this book with you. What is linear response theory? Linear response theory is essentially equilibrium statistical mechanics combined with first order time-dependent perturbation theory. That's how Balakrishnan, who wrote a very nice book, describes it. The fundamental importance of the linear response regime is as follows. If a system is in thermal equilibrium, is perturbed by a weak external force, it was a weak force, linear response theory enables us to determine the departure from equilibrium to first order in the external force. That's basically what it is. Equivalently, when the external force is switched off, linear response theory tells us how the system relaxes back to thermal equilibrium. And this is a very important part of the problem. How it relaxes back to thermal. In fact, Zwanzig's work, Mori's work, and Lee's work, they all show us that if you perturb a system, many-body system, under the protection, so to speak, of linear response theory, you will be able to calculate how that perturbation relaxes over time, how the effect of that perturbation relaxes over time in the system. And that is what he means when he says relaxes back to thermal equilibrium. So relaxation processes that happen in many particle systems return to equilibrium of a perturbed system is something that we can experimentally study. And because we can experimentally study it, this is where the experiment and the theoretical calculations based upon whatever path you follow, Zwanzig's path, Mori's path, or Lee's path, can be compared. So suppose I take the same lid and I expose it to a weak beam of neutrons. So the neutrons are, of course, neutral particles. And the neutrons essentially would treat the atoms sitting here as small repulsive centers, essentially. Neutron beam comes in, and the neutron beam would then get scattered out. So by looking at the scattering of the neutrons, I can construct information about the lid and how this lid was affected by the neutrons, but not so affected that it melted or anything happened within the linear response regime. So the scattering, time-dependent scattering that happened of the neutron beam with respect to this lid can be obtained experimentally. And the very same information can be obtained also theoretically. How? I know the Hamiltonian. The perturbation detail doesn't matter. It is linear perturbation. So by studying the dynamics of some variable here, I can calculate how that variable relaxed from the perturbed state to equilibrium. And then from that information, I can construct the scattering detail of the system. This is where experiment and theory would meet. And if the two agree, then you know that not only your theory is right, your Hamiltonian is right, and your understanding of the processes that transpired to get you back to equilibrium is also correct. So one of the comments I want to make here is when we study linear response theory, our focus, therefore, is in relaxation function, which I'll define later. It's a dynamical correlation function. But our focus is to calculate the relaxation function. What we don't get out of that study, no matter how powerful and insightful, how rich the theory is, what we don't get is, if you ask me, can you actually make a movie of what's happening inside the material? Now that you have been able to compare theory and experiment, I'll have to bail out and say, no, I cannot. Because that information is not really retrievable from my calculation. My calculation would be designed solely to capture relaxation behavior. That's what the theory does. This is where stochastic description can be advantageous. Why? Because you see, in the stochastic description, I can actually go to the dynamical variable and I can actually work with it with a little bit more penetrative power than in the Hamiltonian description. And as a consequence, it may be, I'm not saying it is, it may be possible to get a more visually obvious description of the dynamics inside the system. It may be possible, but this is really not possible using the rigorous approach. And this is a big problem in dynamics. In fact, people are fighting everywhere, almost killing each other, because they disagree on what's happening inside the material. Okay? Scientist A has this theory, this fancy variables. Scientist B has another theory. Scientist C has another theory. And if you go to a meeting and you find all three of them, my God, it's like 3 different catfights going on. Because we cannot really poke our heads in and see what's happening inside these materials. It's such a difficult problem. In fact, there is a great deal of literature on these magnetic systems carrying solitons. Solitons are bundles of energy that doesn't disperse. Great deal of literature. Famous papers. Papers being written for 50 plus years. I'm not kidding. There is still a fight going on whether the solitons exist. And if so, exactly how. Because there is no way on earth any of the techniques we know help us nail this problem. It simply won't. So we can only hope that experiment would advance sufficiently to give us the answer. And we theorists would be chewing our pens because we simply don't have the ability, theoretical ability to go there. And this is the biggest pain in the ass for me as a scientist, because I want to do that, I want to see it, I cannot see. Nature, even for classical system, nature prohibits me from. Now, this disadvantage melts away if you do dynamical simulation. But then you have to do classical problem. Quantum problem, you can't really do a dynamical simulation quite the same way as a classical problem because you have to obey Heisenberg's principle. And that again throws you off. So what nature does and what we can study, ideally, are not the same thing. They are slightly different. We can never understand nature perfectly. And this is the reason why I've had serious doubts as to whether studying physics was a good idea. It was, but no. You just can't get
Too
beyond the
late.
point. Huh?
Too late.
Too late. Yeah, you just can't get beyond the point. Up to a certain point you can, but then you got to bail out. So anyway, the remainder of the paragraph here has to do with the importance of correlation functions. And correlation functions, essentially, if you Fourier transform them, you get the response functions. And these response functions are the ones that you measure experimentally. That's what he's pointing out. We'll come to that in more detail down the road. Right now, it's not necessary. So let me now lay down. I don't have much time, but let me just lay down the sort of favors on the road, so to speak, a little bit. Because solving the Liouville equation for many body systems is now what we are after. That will be how we'll start. And it is understood that our system is a canonical ensemble. It's a large system, many particles. At least that is the assumption. We can reduce the number of particles. That's not a problem, but we'll assume that it's a large number of particles. System has a volume V, system has n particles or spins or whatever it is. And this Mori-Lee theory, which is what I have here, as I mentioned, it's also called the continued fraction formalism. It goes by many names. Continued fraction formalism is as common a name as Mori-Lee formalism. The idea here is to first write down the Liouville equation. So we are writing down the Liouville equation here. And the Liouville operator is defined in multiple ways. One way of writing the Liouville equation is by writing I being square root of -1, IL A of t. That's one way. Another way is by writing L A of t. So the I is sucked into L. So it depends upon how you define it. I just chose one definition. It is not the only definition. And this ILA, this piece here, is basically the Poisson bracket of H and A, which is, as I said, this is the definition. And if it is a quantum mechanical system, then this ILA is I over H bar. Sorry, it's 1 over H bar, commutator of H comma A. I'll give you this notes. Don't worry about it too much. Whatever you write down should be primarily because you're trying to understand it. So our job is to actually solve this equation for some dynamical variable of t, but the solution should be framed in the canonical ensemble. Okay, because these are just operators in general. Classically, operator is not a problem, but quantum mechanically, operator is a problem because it's not an observable. You have to construct something observable out of it. So, but we will, that's why there's a certain level of abstraction in this approach, because you are solving a problem for operators. And once you have solved the problem for operators, you have to convert that information appropriately to what is observable, because it may not be an observable. Now, one important thing is that the Liouville equation at some level is trivially easy to solve. Why? Because you have a first order equation dI dt, which is IL A of t. That means if you can directly integrate it out, and if you directly integrate it out, then you essentially get this e to the ILT A from t equal to 0. And then ILT, because it is a commutation relation or a Poisson bracket relation, yields itself to a description like this. To the H is the Hamiltonian. E to the IHT, A at t equal to 0, e to the minus IHT. And if you expand it, and that's what I had scribbled here, which you can see, it essentially gives you a Taylor expansion with nested commutations. So it's like 1 plus I H A comma H in classical system times T. Okay, plus or maybe 1 minus. I have to look up how it works again. And then it will be A comma Poisson bracket A comma H. That's it. Then it will be A comma A comma A comma H. That will be third order, and so on. So if you expand it out, you will be able to formally construct a solution. And that will be a short time expansion because it's an expansion in time. So if you're going to study long time behavior, which is typically what we're interested in, long time behavior, many decades after the system was initially perturbed, how it is relaxing back to equilibrium. If you want that information, which we typically do, then this short time expansion is inadequate. This doesn't help us. I mean, at most, how many orders will you do? 10 orders, 20 orders, 30 orders? Your computer will probably crash by the time you get to 20 orders, 25 orders. That's still T of the order of 50, nothing. That's the reason why short time expansion is not the best. By the way, when you do molecular dynamics in a system, evolving atoms, you are actually doing a short time expansion. But there you can go to long time. Why? Because the expansion is done using a special algorithm that allows you to time advance with higher accuracy than minimum accuracy. And there are algorithms like Gear algorithm, G-E-A-R. Charles Gear invented that algorithm. These are called predictor-corrector algorithms. You predict and then you correct. You predict and you correct. The next step, the next step, the next step. And in these algorithms, the velocity and the position variables advance with equal accuracy. In a normal algorithm, the position variable accuracy will be higher than the velocity accuracy. But these predictor-corrector algorithms are special algorithms. So you can do short time expansion and go forward without incurring much error. You incur some error. And that is the reason when you simulate something for 10 billion time steps, you have to watch out and be careful that your errors haven't piled up. And there are algorithms to help you. And we use that all the time. So anyway, that's in molecular dynamic simulations. In our studies now, we will do something quite clever. And this is, of course, where Mori came in. We will actually not solve this problem as a time expansion. We would solve this problem in a Hilbert space, in a different space. Now, what is a Hilbert space? A Hilbert space, very simply, is a vector space. Space of vectors. But a Hilbert space has one additional attribute. And that attribute is, how do you multiply two of these vectors? So what is a scalar product? Okay. So Hilbert space has two vectors, let's say, A and B. The question is, how do you multiply A and B? What is the inner product or scalar product of A and B? So instead of solving this problem head on, we are going to take the side route. What is the side route? We will say A of t, our variable of interest, is an expansion in d-dimensional space, Hilbert space. And in this expansion, every term has all time information. There is a coefficient that is valid for all time. And there is a vector that is going to be the vector in this Hilbert space. So for nu equal to 0, you have A0 of t, F0. Then next you have A1 of t, F1, and so on. But these vectors have to be orthogonal, not orthonormal, orthogonal. That means F0, F1 in a Hilbert space, inner product should be 0 because they're orthogonal. F0, F2 scalar product should be 0. F1, F2 scalar product should be 0. All these scalar products should be 0. When would they not be 0? F1 scalar product will not be 0. F2 scalar product will not be 0. Because that is like the length square of a vector. Right? Length square of a vector cannot be 0. That vector will have a certain size. So we will think about A of t as a d-dimensional expansion. I don't know what d is. That information will come from the Hamiltonian when I solve the problem. That's how this theory is structured. So the set of F nu is a complete set of orthogonal basis vectors. They're time independent. See, there is no time here. So you can think about a vector space. This may be your F0, this may be your F1 vectorially. This may be your F2. Then we can't visualize anymore. F3 would be in fourth dimension. So these are your basis vectors and they're fixed. They don't move. But their contributions to the dynamics moves because these coefficients are time dependent. So at some times, some of the vectors will become 0, the contribution to A of t. At some other times, it may be quite strong. So how these A nu of t's evolve, multiplied with F nus, will fix what this A of t will become. Non-trivial problem. And this A nu of t's, by the way, which are time-dependent coefficients, in this theory, this A nu of t's will connect with the correlation functions that I mentioned here. This A nu of t's will be directly tied to the correlation functions. So therefore, if you could solve this problem, even if you can't solve for every f, if you can somehow solve for A0 of t alone, I'll be able to convince you that you have all the information you need to solve this problem. Because remember, you can't visualize. So solving beyond a point may not help you. So this is a very interesting problem because it is a very, very difficult problem at one point. And it's also by the same, in the same vein, it is a problem that can sometimes be solved. So when I first started to learn this, there were about 6 or 7 exact solutions using this technique for simple many-body systems that were developed. Number is much more now. But the fact is, you can solve a problem that you couldn't solve for hundreds of years before that. That itself is amazing. And you can get insights. These are exact solutions that you can generate, or near exact solutions. You get this tremendous benefit. And of course, if you make the stochastic approximation, these problems carry memory. All memory is carried correctly. But if you make stochastic approximation to say that you have delta function memory, they all go to your stochastic anybody problem. So even that provision is built in, at least to a point, which is why I decided to start at this point, rather than start step by step. Because it gives you, it takes you to the top of the building first, because it now gives you an eye view of what's below. And then you can go and study that below point in detail if you want, using various techniques that have been developed for stochastic systems alone. But to understand stochastic systems, you can really do it from here. I'm out of time, so I'm going to stop here. But the next thing that I want to do is I want to tell you how to construct these Fs and As. But before that, we will define the scalar product, because the scalar product is how temperature comes into the problem, because thus far, we don't have temperature. But now what we'll do is we'll parameterize F nu as a function of beta and A nu as a function of T and beta, T being time, beta being inverse temperature, 1 over kT. So we will parameterize the right side in terms of T and beta. And this parameterization will be such that if you could calculate everything perfectly, your beta would drop off. How brilliant is that? That means you took the problem, you went to a room, your canonical ensemble room, you solved the problem in the canonical ensemble, you solved it completely, temperature dependence went away, you brought it back out of the room. It's as if you have only solved it outside the room for any case. So the parameterization is in terms of temperature, and this was introduced by Kubo. And this is called Kubo scalar product. X and Y is like A and B, F nu, F mu. And this particular scalar product also happens to be how susceptibility is defined. So Kubo took the susceptibility formula. In fact, he defined it and made it into a scalar product. And Mori used that. But this is a choice. I don't have to make this choice. In fact, there are cases where this choice is not the best choice. You can take any scalar product you want, because it's like entering which room. You want to enter room number 1, room number 2, room number 3, the scalar products change. So that is one of the discoveries that you can make as to find a better scalar product than Mori and Kubo used. Mori used primarily Kubo scalar product. But this is a whole different discussion, and I want to go a little slowly. And some of this I want to go on the board also. But we'll see how Tuesday is shaping up. We might do it like this, or we might move to how much of this versus that I have to do, and then we'll take a call as to how to proceed. I think we should be able to put a laptop facing the board, Tony, don't you, for Vivek to follow? Probably try that. Put it on one of the chairs. No, you are muted. You're still muted. Now you're okay.
Can you hear me? It should work
Okay.
if it was for the Blackboard. That should work.
Yeah, I think it should work. We'll I'm pretty sure we can make it work somehow or the other. As long as I don't write maybe in the whole blackboard, but part of the blackboard, it should be possible.
Mhm.
Yeah. Any questions?
Well, not yet.
Okay, good. We'll talk about this on
Yeah.
Tuesday. Huh? Good.
Yes.
Have a great weekend. Today
Thank
it
you,
worked
Professor.
out. Yeah, very welcome. All right,
Yeah.
bye-bye. Take care, Vivek.
Bye.
Take care.
Yes.
Bye. I'll give you some reading also. I'll mail it up.
Yes, it was a very good lecture actually.
Well, thank you. You got it right,
Yeah.
more or less where I'm going.
Yeah,
Great.
I actually, loving it. After my coursework, this is the first time I'm studying physics now again, so it's a good thing.
Yes.
And classical mechanics has always been my most favorite subject. So
Classical mechanics is a lot of fun. That's
yeah,
why I like classical mechanics. Quantum mechanics really makes me very nervous.
yeah, understandable.
I did my PhD on quantum mechanics. I stay away from it. It's mostly very complicated. All right, I'll let you go. It's very late for you. So go
Yeah,
to sleep, and I'll.
yeah, it's okay.
Okay,
Bye.
good
Good
night.
night.
Good night.